The main similarity theorem in the beginning of this chapter says that if I have a triangle ABC, so like this triangle here, and if I draw in a line which is parallel to one of the sides of that triangle, so I draw in the segment DE here, which is parallel to BC. So that we start out with this assumption of parallelism in this triangle. We assume that DE is parallel to BC. And the conclusion of this theorem is that then the smaller triangle, ADE, try and get this in here, so the purple triangle, ADE, and the original big triangle, ABC, are in fact similar. So that's what it does, is it gives us a way to create similarity by using parallel line segments. So parallel implies similar. And we're able to prove this, as you sort of discovered when you read through and annotated this proof. What were the key ingredients that went into the proof of 3.2.4? So the midline theorem, 2.4.2, I think was the midline theorem, was exactly this theorem, just in the case where AD and DB were congruent and AE and EC were congruent. So if that was the case, then we have the midline theorem that actually gives us this result. So we have that additional assumption. But we don't have that assumption in this case, and so we get a more general result. The first element that's explicitly called upon in this proof is lemma 3.2.1. And Raquel has looked at this and said that it gives an understanding of how D and E are midpoints, although they're not exactly midpoints unless we're talking about the midline theorem, and how those two corresponding sides are equal. So lemma 3.2.1 in particular seems to be an important element to the proof of 3.2.4. So let's put that on the board here as one of the important elements that we're going to have to reckon with. So we'll look back at what the statement of that lemma is in just a moment. But lemma 3.2.1 doesn't actually tell us anything about similar triangles. 3.2.1, so here's what 3.2.1 says. It says that if I have a triangle ABC, so I'm going to sketch in a triangle here, ABC, BC, and that if I take points D and E and I place them on AB and AC, so D is, say, here, and E is maybe here, and if I place them on those two sides in such a way that DE is parallel to BC, so there we have again the assumption of parallel, then we conclude, so parallel, then we can conclude this thing that's in the square right here, AD over DB equals AE over AC. So my question, to get us started thinking about this, is how is this lemma different from theorem 3.2.4 that we just proved? Because it seems like a lot of the same ingredients are going into it. So in both cases, both in 3.2.4 and in 3.2.1, we begin with a triangle, ABC, and we begin with another line which is parallel to BC. So the parallelism is actually a part of our assumption, both in 3.2.4 as well as in 3.2.1. Right here we start with a triangle, and we assume that DE is parallel to BC. There is one subtle difference in the assumptions in 3.2.1 and 3.2.4. So we have a triangle, we have a parallel construction, but what's slightly different in these two statements in the hypothesis of the theorem? That's something that the author makes different between these two proofs, is that in both examples, they say, let's let D be a point on AB, which I would interpret to mean that D is between A and B. And so we get a diagram that looks just like the diagram that we have down here. To me, saying that D is a point of AB really obviates these other two cases. The other two cases that the author considers here is, well, what if D is out here, let's say? So it's on the line passing through A and B, but it's not between A and B. So that was one of the cases that I just erased from over here, and so the proof would be similar, but not exactly the same necessarily. But I would interpret the statement of this theorem as already assuming that case 1 is the only case that we really need to care And because the proofs are analogous, we're not going to lose anything just by assuming that that's what it means, both in the case of 324 and in the case of 3.2.1, which let me put that one back up one more time.
Yeah, I feel like saying that D is an array of AB is kind of irrelevant.
It's too much, because look, he actually uses the same language here in the statement of 321. D is a point of AB, and so he's at least. But then again, he also has three different analysis figures on the next page that show the different possibilities of where D might be situated. So again, because the proofs are all analogous, I don't think that's a detail that we need to sweat. So, in fact, the hypotheses in lemma 321 and 324, 3 and 324, are exactly the same. We start with a triangle, and we start with points D and E that lie on the lines, or we're going to interpret them as the segments, defined by AB and AC. And we assume that DE is parallel to BC. So all of our assumptions are exactly the same. So if there is a difference between these two theorems, the difference is going to be in the conclusion. So what's the difference in the conclusions here? 324 concludes this, and 321 concludes that. What's the difference?
Segments in the line.
Okay.
Are equal to each other.
Right. So 3.2.1 asserts that there are two equal proportions. So if we draw the triangle over here again, so here's ABC, and then we'll put D and E, I don't know, let's say here, D and E. And so the two equal proportions that are being set up, I'll try and draw this in a way that makes sense. AD on the one hand, right, so that's that numerator, its ratio to DB. So DB here is not actually a side of a triangle. DB is just this little length right there, this little excess. So the ratio of AD to DB is being compared to the ratio of AE, so that is legitimately a side of a triangle, AE over there. Its ratio to EC, which again is not a side of a triangle, but just an auxiliary segment here, EC. So it sets up two equal proportions, but they're not all proportions of sides of triangles. They're proportions of a piece of a segment, which is a side of a triangle, to the remaining piece, which is not actually part of a side. Well, it's a part of a side, but it's not the whole side of that triangle. So how is that different from the assertion in 324 that the triangles are in fact similar? What information goes into the triangles being similar? What has to be true by definition?
Congruent angles.
Mm-hmm. So congruent angles. And?
Isn't it proportional? Something about proportional?
Okay, yeah, the proportional is the important part. So congruent angles and proportional sides. How many proportional sides?
2.
I would say more than 2.
3.
Yeah. So all 3 sides need to be proportional. And so there's 2 things that make this a stronger statement. First of all, we have to have 3 pairs of proportional sides, and in 3.2.1, we only were setting up 2 equal proportions. Right? So we need 3 equal proportions here. And the other thing that makes it stronger is the word sides. Right? In 3.2.1, one of the lengths that we had in the denominators of our proportions was not the length of a side of a triangle, it was the length of a piece of a side of a triangle. Right? So 3.2.4 really is a stronger result than 3.2.1. But because they're so similar, it's maybe, pun intended, it's maybe not surprising that 3.2.1 plays an important role in this proof. So we need 3.2.1, but we also seem to directly need the definition of what it means for 2 triangles to be similar. Looking at how 3.2.1 gets used in this proof, because the setup of this theorem and the setup of lemma 3.2.1 are exactly the same, it means that we can just directly apply 3.2.1's result to this triangle. And when it's done, we get to conclude exactly the conclusion of 3.2.1, which is that there is an equal proportion between AD and DB and AE and EC, just like lemma 3.2.1 said. But then what happens after that? What is the author really doing next with the result of 3.2.1? So what's all this garble? Yeah. So yeah, the first step that's taken, let's go one of these at a time. So the conclusion of 3.2.1 gives us the equality of these two ratios. What then happens to go from this line to the next line? You see what he's doing there?
He just flips the fraction.
Yeah, just take the reciprocal of both. That's just an algebra step. That doesn't have any geometric consequence to it. And so it really is this next step that is the most subtle. It's one of these things that if you're trying to prove this for the first time, you might not think to do this. So this is an important connection here. So looking at what people wrote in the comments about this, why are we adding 1 to both ratios? Says Hannah, and I agree. Why would we want to add 1 to both ratios? And so, Olivia, can you tell us can you give us the summary of what you said in reply? So when I read this, here's what I see. Lemma 3.2.1 is awesome, except the big limitation that it gives us is it doesn't give us a ratio between sides of triangles, right? AD really is a side of one of the triangles that we want to prove is similar. AE is also a side that we're interested in showing is similar. So AD and AE, we want those to be part of our logic, because we want to show that the sides of two triangles are proportional, and those are really sides of triangles. But DB and EC are not sides of triangles, right? DB is this funny little segment over here. EC is this funny little segment over there. Those aren't the sides of the triangle ABC that we really would like to prove something about. And so we have this problem that exists in the denominators of this fraction. Namely, the problem is that these denominators are not sides. And because they're not sides, we need to do something to transform those segments, those side lengths, those little segment lengths, into the side lengths of the big triangle ABC. And we can't do that with fraction arithmetic as long as the problem is in the denominator, because when you add fractions, the denominators don't change, right? So we need to make it so that we can combine the lengths of these little segments with the lengths of something else that can get us to the length of the whole sides AB and AC. So we have to flip the fractions so that when we do fraction arithmetic, we can get an AD to combine with the DB to give me AB. Right? Because at the end of the day, what we really need to know something about is all 4 of the lengths in this expression need to be sides of triangles. Sides. Sides. So that's the bigger narrative behind what this computation is accomplishing. We have something the lemma gave us which doesn't have 4 side lengths. It has 2 sides and 2 segments of sides. And then we need to do something in order to patch up the remaining lengths in those sides that we didn't have. We need to extend DB into AB. And we need to extend EC into AC. And so we're missing these highlighted in red portions. But we can get them by adding 1 to both sides of this equation, and this is the genius of this proof, right? Adding 1 to both sides is a surprising step. But doing that and then using common denominators for fractions means that when I add 1 on the left-hand side, it's the same as adding that AD length in the numerator. And when I add 1 on the right-hand side, it's the same as adding in the AE length in the numerator. Because those two sides of the equation have different denominators, we get different additions in the numerator when we add 1 to both sides. And doing that exactly patches up the length of the remaining side. So at this point, we have 2 proportional sides in the triangles that we're trying to show are similar. AB and AD and AC and AE have the same proportion one to another. But we can't stop there, because being similar requires what? It requires that third side to be proportional too. So we also need to show that the proportion of DE to BC, whatever that proportion happens to be, needs to be the same as the proportion that we found between the other 2 pairs of sides. We don't know that yet, so we need to bring that third side into the conversation. And it's not immediately clear how to do that, because all we know about DE at this point in the proof is what? All we know is that DE is parallel to BC. That's the only information that we have. And so if we need to say something about the length of DE, we need some tool which will allow us to talk about the lengths of 2 parallel line segments. So what does that tool end up being in the author's proof? if you look down what's on the screen here. So the one thing that we know about parallel line segments is if they are opposite sides of a parallelogram, then what are they? They're congruent. And so that's the tool. That's what the author is looking at this diagram and seeing. Is, well, I only know that they're parallel. I don't know that they're congruent, and they probably won't be congruent, right? DE in our figure is certainly shorter than BC. Right? But if I can get a parallelogram into this picture somehow, then I can begin to make such an argument. So he constructs this new segment EF. And the segment EF is constructed in a way such that EF is parallel to AB. So F here is the point where the segment parallel to AB passing through the point E. That segment is uniquely defined because of the parallel postulate, remember. F is the point where that segment meets BC. And this was another thing that a bunch of people highlighted. The author jumps straight to saying, because DE is equal to, because BDEF is a parallelogram, therefore DE is equal to BF. So, how does the author know that BDEF is a parallelogram?
DEF and DE is congruent to BF.
So, how do we know that the opposite sides are congruent? We don't. If we knew it's a parallelogram, then we could conclude the opposite sides are congruent. But if we don't know it's a parallelogram,
You have to go after the angle measurements.
Okay.
And using that, the lines are parallel, therefore the lines intersecting them become a transversal.
Okay.
Making angle B and angle BEF congruent, and then the
So-
same argument for the other.
because
set.
then those would be alternate interior angles,
Yes.
and these would be alternate interior angles. And so we have two pairs of opposite congruent angles. Is that enough
Yes.
to make a parallelogram? How do we know?
Parallel and congruent. Oh, the theorem?
We had a theorem. In fact, we had a theorem that we didn't need to chase all those angles around just now in order to use. It would be fine.
Didn't we just need one condition out of the three?
We need one condition out of the three, and the three conditions that we had were,
This wasn't that your proof?
the three conditions were having opposite pairs of congruent angles was one of the ways to do it. Having one pair of opposite and congruent sides was another way to do it. Is there one more? Having two pairs of
One had to be parallel and congruent.
one pair being parallel and congruent, or all opposite angles being congruent, or two pairs of opposite sides that are congruent. I don't think we have any of those unless we do this opposite angles argument that you just mentioned.
Right, I was just gonna say that, but we don't have like any of that information yet, right?
We don't have any of that information, but you can make the argument using opposite interior angles, as you were saying, treating ED and BC both as transversals to the parallel lines AB and EF, right? And then chasing those angles around. But I think that we're hitting a fly with a sledgehammer on this. What's the definition of a parallelogram?
Opposite sides parallel.
Opposite sides are parallel. Well, we have one pair of opposite parallel sides, DB and EF, by construction. What about the other pair? How about DE and BC?
They're parallel.
How do we know they're parallel?
Midline theorem.
No, because the midline theorem doesn't apply unless D and E are midpoints.
Isn't it given?
Yes, it's given to us in the proof. In our assumption about this diagram, we assumed that DE and BC were parallel. In fact, we haven't used that assumption in our proof until now. Right? But now it gives us the very definition of parallelogram. We have two opposite pairs of parallel sides. So, two pairs of opposite parallel sides.
So we know DE is parallel to BF because it's given.
DE is parallel to BF or BC, right?
BC.
Because that was the assumption in our in the hypothesis of the theorem. That's how we constructed DE in the first place. We chose points D and E on the lines defined by AB and AC such that DE is parallel to BC. So we knew that. That's part of the identity of the points D and E, is that parallelism. And we constructed EF in a way that made it parallel to DB. So that's how F came into being, is by having that parallelism as part of its identity. And so all of the parallel pairs of sides in this figure we got either by assumption or by construction. And that's the original definition of parallelogram. So we don't need to go through the theorem, although we could have applied the theorem by chasing around opposite interior angles, as we just did. So just to conclude this proof then, how does this being a parallelogram get us to where we want to be? How does the author get this ratio down here at the bottom of the screen? AC over AE is equal to BC over DE.
Well, if DE is equal to BF, you can switch out in the ratio up top. So instead of BC,
Instead of
a ratio to BF, it's a ratio to DE.
Okay, so the author is starting here with this ratio that nobody called out in their analysis, but it starts with this ratio. AC over AE is the same as BC over BF. Why? How is the author getting that set of ratios? What does he say about it? The author says using an argument similar to the one above. Just this time using EF as my parallel segment and considering the triangle CBA and potentially CFE, I suppose. But yeah, applying lemma 3.2.1 again gave us those ratios. So 3.2.1 is coming back at us one more time in this proof to give us a new set of ratios, and then using the congruence of BF to DE that we get from the observation that this is a parallelogram, and therefore it has opposite pairs of congruent sides by a theorem that we had in Chapter 2. We can trade out, as you said, BF for DE, and then get the ratio of BC to DE to be the same as the ratio of AC to AE, but that was exactly one of the ratios in the conclusion that we had up here. Right? AC over AE equals BC over DE. And so, in fact, it is true that all three of those ratios are equal, which is what we wanted to show in order to show that these were similar triangles.